Greetings everyone. We are starting with day 5 of Pfizer AgTech workshop on data analysis and clinical research. Before the start of the program, we have some housekeeping rules such as question and answer will be at the end of the session. To ask question, we request you to raise your hand through Zoom, followed by which our team will pitch you in for interaction. Kindly keep your phone on silent mode. Kindly unmute yourself and keep your video on during presentation. Requesting to mute yourself while not in discussion. Requesting speaker to complete your talk in stipulated time. Now to initiate the program, I would like to invite Dr. Jayan Goda, Program Director, Panacea, Professor, Department of Radiation Oncology, Tata Memorial Center, Mumbai. Dr. Jayan, over to you.
Thank you very much, Rohan. And a very good afternoon to all the speakers and the participants of this particular workshop, Panacea 2022 on data analysis and clinical research. So we have been having this webinar for the last 4 weeks, starting from April 16th. And now we are in the month wherein we are talking about biostatistics. And as oncologists, we should know the importance of biostatistics when we are doing any analysis for observational studies or for clinical trials. Today, we have got two eminent speakers with Dr. Ashish Yadav and Dr. Atanu Bhattacharya, who are going to talk about sample size estimation in clinical trials. Sample size estimation in clinical trials is another important fact which needs to be kept in mind by all the oncologists, or for that matter, any clinical researchers, when they are trying to develop their clinical trials. So without much ado, I would like to ask Sanchita to introduce our speakers.
Thank you so much, Dr. Jayant. So we begin with our first topic, that is sample size estimation for clinical trials. And we have with us today Dr. Ashish Kumar Yadav, who has completed his PhD in medical statistics and is currently the assistant professor in the biostatistics department at Banaras Hindu University, Varanasi. Dr. Ashish has more than 25 publications in reputed national and international journals, and his research interests include study design and survival analysis in clinical trials. I would now like to welcome Dr. Ashish to begin with his talk.
Thank you, Sangeeta, and good afternoon to all the participants. First of all, I am thankful to Panacea team, Professor Jain sir, and my friend Atanu for giving me this opportunity to share my view on the sample size estimation. And with this, I would ask whether we should start the presentation, Sangeeta.
Yes, sir, you can share your screen.
Yes,
Okay.
Dr. Ashish.
Okay, we'll start the sharing. I hope the screen is visible to all.
Yes, sir.
Yes.
Okay. So we'll begin with the sample size determination. Sample size basically is a heart of statistics. And this is one of the most important reason behind the popularity of statistics in any stream, be it a medical, be it a field of sports, be it a field of a business, anything. Why? Because no one is interested in the raw data set. We all are interested in the characteristics of the data set. What is the characteristics of the data set? And with the help of the small sample, we try to measure the characteristics of the data set. So how we are choosing that sample, that is termed as, in scientific term, we call it as sampling. And how much we are choosing, that is called your sample size. So these are two important ways with the help of which any sample if chosen in a scientific way and if chosen adequately, will be the representative of the population and will save a lot of money and manpower. And the estimate drawn from the sample will be as good as that of the population. So let's begin with the introduction part. Okay. So one of the most important factors to consider in the design of an intervention trial is the choice of appropriate study design, study size. Studies that are too small may fail to detect important effects on the outcome of interest, and the studies that are large then necessity are waste of resources. Not only that, if you are choosing a very small sample size, you may not have the true inference of the population. And if you're choosing a lot of large, bigger size, very big size, then what will happen? Even a small deviation will indicate that there are significant findings. Okay, so it is very important that we should have an optimum size. Okay, so statistical methods are available for estimating of appropriate sample size depending upon the type of outcome measures, expected disease rate or size of the effect, study design, and the requirement of confidence interval or the precision which one observer wished to have in his study. So in this short presentation, I will try to demonstrate various methods of sample size calculation available for different types of study designs under different scenarios. So an investigator planning to conduct a clinical study must properly define the objective of the study before consulting a statistician. The statistician then can transform the objective into statistical hypothesis, the null and the alternative. So all of you must be knowing that hypothesis is nothing but it is a assertive statement or a scientific statement about a random phenomena, which can be stated in two broad areas. One is referred to as the null hypothesis, which conveys a no difference meaning, and the second one is your alternative hypothesis, which conveys a difference of opinion is there. One of the difficult tasks for a statistician is to convince the investigator that while making a decision, one is liable to commit an error, no matter how careful the experiment is conducted and no matter how careful the observations are collected. Since it is a random phenomena, the outcome is uncertain, so one is certain to have some type of error and we need to control that error. So first thing that statistician has to do is that it has to make the clinician aware that whatever the inference we are going to make, this will be having some amount of error which we cannot avoid. So we need to fix that type of error. So we will be seeing in detail what type of error can occur. Now, once the statistician and the clinician have a collaboration on the type of error and how much risk they are willing to take, there are three important questions which generally a statistician asks clinician while calculating the sample size. If the first step of convincing the investigator is over, then the statistician proceeds to make inquiries on the following 3 points. First question is that how big is the risk the investigator is willing to take when the null hypothesis H0s get rejected, even when H0 holds true on the basis of the results of the experiment. That means, in short, it says that the first question which a statistician wish to ask from an investigator is that how much risk he is going to take if the probability of rejecting the null hypothesis when it is true is there. Okay, so that probability is generally in statistical term we call it as the probability of type 1 error. So probability of type 1 error is what? It is nothing but it is rejecting H0 when H0 is true. Okay, so whenever we are rejecting something which is true in nature, that is referred as type 1 error. And generally in statistical term, we denote it by alpha. So type 1 error is rejecting the null hypothesis when it is true in nature. We call it as a serious error also. So we need to fix it in advance. Okay, the second question which a researcher would be asking to the clinician is that how big is the risk the investigator is willing to take when the alternative hypothesis H1 gets rejected, even when H1 holds true, That means he wants to ask the clinician what is the probability or how much percentage of risk you are willing to take if we are rejecting H1, that is the alternative hypothesis, when H1 is true. So in the alpha, we were rejecting H0, the null hypothesis, when it is true. So how much risk the investigator is going to take, is willing to take. And in the second error, we are asking the investigator how much risk they are going to take if H1, the alternative hypothesis, is true, but you are rejecting it. So we call this type of mistake or error as type 2 error, and it is denoted by beta. So beta is what? Beta is nothing but it is the probability of rejecting H1 when H1 is true. So accepting something which is false in nature is called your type 2 error, and we denote it by beta. So you must be having some idea about the probability. We all are talking about probability. So what is probability in very short term, if I say, or in a very layman term, if I say what is probability? Probability is nothing but it, as in SI, you have the meter, kg for measuring the length and for measuring the weight. Similarly, in the field of science, for measuring the uncertainty, we have the tool called probability. P, we denote it by P. Okay, and you know that the total probability of happening of the events will not exceed 1. It generally lies between 0 and 1. Okay, so once the probability of rejecting H1 when it is true is denoted by beta, then automatically the probability of accepting H1 when it is when H1 is true is nothing, it will be 1 minus beta. And this 1 minus beta is what it is saying, that the alternative is true and you are also accepting it. Then we will be calling it as 1 minus beta, and 1 minus beta, we call it as the power of the test. Higher the power of the test, more reliable your estimates will be, and you would be getting a narrower confidence interval. So we will be discussing the confidence interval also. So far we have seen there are two types of hypothesis, null and alternative hypothesis. Null is a hypothesis which conveys a no difference meaning. Alternative is a hypothesis which conveys a difference of opinion. Similarly, we have three types of broad questions which generally a statistician, before calculating a sample size, will be asking to the investigator. First is the idea about the type 1 error, how much type 1 error one is willing to take. Type 1 error, which is nothing but probability of rejecting null hypothesis when null is true. Second is how much probability the investigator is assigning to the type 2 error, which is nothing but rejecting the alternative hypothesis when alternative hypothesis is true, or you are accepting something which is false in nature. Okay, and from this concept of type 2 error only, we have got 1 minus type 2 error, that is 1 minus beta, which we call it as the power of the test. The power of the test is nothing but it is accepting the null hypothesis, alternative hypothesis, when it is true in nature. The third question is that what is the minimum acceptable difference, delta, between the values of the parameter specified under the null and alternative hypothesis? This delta depends upon variety of criteria involving the clinical and practical significance of difference. Okay, so three questions generally we are asking. First one is the type 1 error probability. Second one is the type 2 error probability, and the third one is basically we would be asking about the minimum acceptable difference. What would be the minimum acceptable difference you are going to take? Suppose the null hypothesis is having a certain value, the alternative hypothesis is having a certain value. So whatever the difference between the null and alternative is there, whether that difference, how much difference you are going to allow in your study. Okay, so let's have a very small example. For example, when the investigators knows that the management would be interested in undertaking the most costly affair of marketing, the test compound T, only if probability of T, which is denoted by PT here, the proportion of improvement on the test compound shows an increase of at least 15% or 0.15 over the proportion of the standard treatment, which is denoted by PS. Okay, he or she sets up delta is equal to 15% here. Okay, so this much is the minimum acceptable difference between the null and alternative. So accordingly, your null and alternative would be fixed. So null would be, it is coming, it is having a no difference, meaning that is PT is equal to PS, that is the new treatment is same as that of the standard treatment, and alternative is your PT should be at least 15% more effective compared to the your standard one. So alternative here would be PT is equal to PS plus delta, or PT minus PS is equal to delta. That is the minimum acceptable difference delta. Okay, now some pre-requirement, general pre-requirements before calculating any sample size calculation in any type of the study. So before calculating sample size, one has to decide on the following. First one is the type of the outcome measure. What type of outcome measures are there? Okay. Second one is the study design. Okay, what type of study design is there, whether it is a observational study, whether it is an analytical study, or whether it is a RCT. So what type of study design it is? Guess at likely the results. Required level of significance. The required level of significance, that means the type 1 error which you are going to fix. Okay, required precision or the power, that means based on the probability of the type 2 error which you are allowing, accordingly your power would be decided. For example, you are allowing an error of 20%, so automatically your power of the study would be 1 minus beta, that means 80% would be the power of your study. Okay, so these are the requirements which before the sample size calculation which we need to have. First is the type of outcome, then study design, then guess at the likely results, required level of significance, and the power or the precision of the test. Okay, now coming on each of the assumptions one by one. Type of the outcome or measures. The statistical methods for sample size determination determines on which type of outcome is expected. Okay, so there are mostly three main type of outcome in which one is interested. First one is your proportions, then we have means, and the third one is the rates. Okay, so proportions, for example, in a trial of a new measles vaccine, an outcome measure of interest may be proportion of vaccinated subject who develop high level of antibodies compared to those who are not having this type of outcome. So we want to compare these two proportions. Second is we might be interested in the means. For example, in a trial of an anti-malaria intervention, it may be of interest to compare the mean packed cell volume, PCV, at the end of the malaria sessions among those in the intervention groups and those in the comparison groups. So here the outcome of interest is the mean. Third one is the rates. For example, in a trial of multi-drug therapy for leprosy, the incidence rate of relapse following the treatment may be compared in the different study groups under consideration. So in rates, we can have incidence, prevalence, or attributable risk, like these types of measures for comparison. So basically, our sample size calculation depends on our objective. What is the outcome variable in which we are interested? If we are interested in the proportions, then the methodology for calculation of sample size for proportion is different. If our objective is for the for outcome variable of interest is the mean, then the sample size calculation for the means will be there, and accordingly for the rates will be there. Now, sampling error. These are the few important terms which we should know before the sample size calculation. Okay, as we have known that one of the main reason behind the popularity of statistics in any field is that one can make a guess. Okay, and that guess has to be a scientific one. A scientific guess can be made. Okay, so in general, we are not interested in the raw data set. No one is interested in the raw data set. If someone is saying that census is going on and this time we have collected so and so much amount of data set, one general question you all people will be asking is that, sir, just tell me whether our population growth rate is increasing, is decreasing, or is it in a stationary phase? What is the TFR? Just one question. So that one characteristics in statistics, we call it as a point estimate. Okay, so we all are interested in the point estimate. Point estimate, that means that characteristics of the sample which is representative of the population, that has to be true in nature. So what is the variability in that sample statistics or the characteristics for the sample which you are measuring? Suppose you are interested in the mean birth weight. Okay, at say at birth, what is the birth weight? And you want to make from the sample, you want to make the inference about the population. So you have chosen a sample. Now that sample has to be representative for the population. Okay, so how we can decide that this sample is having a reliable sample? That sample can be a reliable sample by looking at the sampling methodology and looking at the sampling error. We call it as SE. You can be little bit sure that the estimate or the inference from the sample might be little bit good. So there is often confusion between standard error and standard deviation. Okay, so let me tell you from a very basic layman perspective what is standard deviation and what is standard error. If we call it about the standard deviation is nothing but it is the deviation of each and every values from the central value, which we call it as the mean. So suppose you are having a data which is of size 50, and for that data set you are having a mean value say 5. 50 sample size is there and you are getting a mean value as 5. Then how much each and every value is deviating from this central value which is 5, that deviation is called your standard deviation. That is the standard deviation. Now what is sampling error? Sampling error is the standard deviation is the deviation of xi values, data point values, from the mean values, whereas standard error is the deviation of the sample statistics, that is the mean, from the population mean. Okay, so that means it is giving you an idea that how much your x bar or sample mean is varying with respect to the population mean. Okay, so it is deviation of sample means or sample statistics from population characteristics, which we call it as parameters. Okay, so it is very different from standard deviation. So lower the value of standard error you are getting, more reliable your sample would be with respect to the population. Okay, now coming on the confidence interval. Okay, now in sample size calculation, it is often said that higher the number which we are choosing, more lesser the standard error we would be getting, because it is inversely proportional to the your sample size. Okay, so if you are having a higher sample size, automatically your standard error would be less and your sample would be having a lower standard error value, and it will be said that the sample is more resembling the population. Okay, but how much should be the sample size? Okay, this amount, how much confidence or how much power you want in your inference, that has to be decided using your confidence interval. So confidence interval is nothing but it is your point estimate. For the previous data, if we got a point estimate of 5, say, then with respect to 5, how much sample size we should get, so that if you are saying that we are allowing a deviation of 2 points, that means the sample size can vary, or your parameter, sorry, your point estimate can have a value from 3 to 7. Okay, from 3 to 7, if you are having a narrower width, then you are very much confident about your estimate, point estimate 5. Okay, so this width with which you can make a inference about the point estimate, this is nothing but this is your confidence interval. So in general, the observed value of the outcome measures gives the best estimate of the true value. In addition, it is useful to have some indication of the precision of this estimate, and this is done by attaching a confidence interval to the estimate. So confidence interval is nothing but it is point estimate plus deviations, can be on either side, plus minus the deviations. Okay, so for example, if we say if we want to find out the 95% confidence interval, so this, what it will be saying, this confidence interval would be saying is that it is a range of possible values for the true value of the outcome measure. So that means we are 95% confident that our point estimate will be lying in this interval only. Okay. So if the outcome measure is proportion, for example, from a sample data, and we are denoting it by phi here, the 95% confidence interval for this point estimate phi is point estimate phi plus minus 1.96 into standard error. So standard error, you know that it's a type of a variation of only the point estimate. From where do this 1.96 has come? 1.96 is nothing but it is taken from the normal distribution table. Okay, so 1.96 is the value under which you would be getting a 95% region under a normal curve. So confidence interval, if you have to create a confidence interval, it will be the point estimate plus minus your Z value into standard error. If you want a 95% confidence interval, you have to take Z equal to 1.96. So this 1.96 from the Z table, if you see for standard normal curve Z table, you can Google and you can see that standard normal table. For Z value equal to 1.96, you are getting a 95% region. That's why we are taking 1.96. If someone wish to have a different confidence interval, accordingly he can choose the value of Z. For example, if you are choosing a 90% confidence interval, you would be having a multiplying factor 1.64. For 99%, it is 2.58. From 99.9%, it is 3.29. Okay, so it may sound very fascinating that you are choosing a very narrower confidence interval, but let me tell you, if you are increasing the confidence interval, rather you are narrowing the confidence interval, what you are doing, automatically you are point estimate plus minus standard error. Standard error is inversely proportional to your sample size n. That means you are increasing your sample size n. As you are increasing your sample size, you know that more number of patients who have to be enrolled in your trial, and accordingly you have to invest more money, more ethical issues will be there. So we have to choose an optimum only, so that our money and our time is saved and the inference is also not lost. Significance test in p-value. So the objective of significance test is the nothing but it is a method of testing the null hypothesis. Okay, so it depends on different types of objectives, what type of objective you are having. So if someone is interested in having a comparison of proportions, he would be framing a different type of outcome, and accordingly he would be having a different steps. Okay, but there are some general steps for conducting any type of significant test or testing of hypothesis. We can divide it into 4-6 main parts. The first one is you first have your outcome variable. What is your outcome variable of interest? First step in conducting a testing of hypothesis. Second is that you decide on the level of significance, what level of significance you are going to allow in your study. Generally, we take at 95% level of significance and we allow a 5% error. The third step is that calculation of the test statistics value in which we are interested. It is nothing but it is observed value minus expected value divided by the standard error of your expected value. Okay, suppose we are interested in comparison of mean. So it will be the observed value, observed mean minus the expected mean. Two samples are there, or from the population you are doing it. So from the population mean you are getting one mean, and expected mean is this from the sample you are getting one mean. So this is observed minus expected divided by standard error of your sample mean. Same goes to whether you are doing an association check also. The steps remain same. Observed value minus expected value divided by expected. Only the thing is that if you are doing for checking for association, you would be having a different distribution. In that case, you would be having a chi-square distribution. Similarly, if you are checking for comparison of mean, you would be having a t distribution if your sigma is unknown. Okay. And your p-value, what is p-value? P-value is nothing but from a layman term, if I say what is p-value, p-value is giving you an indication that how well your data goes with the null hypothesis. Okay, so if your data matches well with the null hypothesis, that means the matches well, that means you are having a higher probability value. So if you are having a higher probability value, automatically your data goes well with the null hypothesis and your null hypothesis will not get rejected. Okay, so how much would be the p-value? That has to be decided by the investigator before conducting the study. Okay, so generally it is the upper tolerance limit of the type 1 error, and in most of the studies alpha is taken as 5%. So if the study matches well with the null hypothesis, you are having 96%, 97% matching, automatically your p would be having a higher value and your null hypothesis will be not rejected. If your data does not goes well with the null hypothesis, that means it is not matching with the null hypothesis, then automatically you will be having a lower probability value for your data to match the null hypothesis, and in under that circumstances you can say that at a given level of significance your null hypothesis is rejected. Okay, so in this example you can see that we are having a p-value of 3% only, and we have fixed a level p-value at 5% only. So here we are seeing that we are getting a lower p-value. This is an indication that our data is not matching with the null hypothesis. So automatically we would be making an inference that at a given level of significance our null hypothesis is getting rejected. The smaller the p-value, less possible the null hypothesis seems as an explanation of the observed data. Okay, so while a small p-value can be interpreted as an evidence of real difference between the groups, a large non-significant p-value must not be interpreted as indicating that there is no difference. It merely indicates that there is insufficient evidence to reject the null hypothesis. So it might be that you might not be getting a significant finding. It might be because of the small sample size or the faulty study design you have chosen, or you are not having the adequate sampling frame. So it might be an indication of that thing. Okay, a significant p-value also might indicate these things. So one has to take care of while framing a study design, one has to take care of the study design, objectives, sampling, techniques, sample size estimation, adequate samples. Power of the study. The concept of powers comes into play when the focus of the study is to find out whether a significant difference exists between two groups. Okay, so a power of 80% to detect a difference of specified size means that if the study were to be conducted repeatedly, a statistical significant results would be obtained 4 times out of 5. So if your study is powerful, your study is having a power of 80%, that means out of 5 times, if you're repeating the same experiment, you are likely to have the same outcome 4 times. That means a significant p-value. So if you are having high power in your study, automatically your study would be having a narrower confidence interval. So when deciding a study, the objective is to ensure that the study size is large enough to have a higher power if the true effect of the intervention is large enough to be of practical importance. So power depends on certain things. First is that what is the effect size? Second is the study size, how much n you are increasing, you are taking in your study sample. Okay, so first it depends on delta. Second, it depends on the study size n, and third is the what type of testing you are doing, whether you are doing a one-sided testing or a two-sided testing. In general, two-sided testing is more powerful compared to a one-sided testing, but it depends on the objective, what type of alternative hypothesis one is having, one-sided or a two-sided hypothesis. One-sided and two-sided test, let me in one line just say what it is. If you are conducting a superiority trials or inferiority trials, generally we are looking at the one hand only side, superior one right hand side, or the inferior one left hand side in a normal distribution. But if you are not having any idea about the test being conducted of the nature, so we have to consider the both hand side. So in that case, it has to be a two-sided test. So in case of a dilemma, when one is not having any idea about the outcome, what value it can take, generally it is safe to have a two-sided testing compared to a one-sided test. Okay. Now, choice of the criterion. The choice of which of the above two criterion, precision or power, should be used in any particular instance depends on the objective of the study. If it is unknown, two scenarios will be there. Okay. So first one is that you are doing testing and it is completely unknown what is going to happen. So if it is unknown that the intervention has some effect, it makes little sense to test the null hypothesis, and the objective may be to estimate the magnitude of effect and to do this with acceptable precision. Okay, so magnitude of effect is coming here, and with acceptable precision. And the second scenario is that it is you are knowing that the intervention has an effect, but you want to know the width of or the effect of intervention. Okay, so usually it is more important to estimate the effect of the intervention and to specify a confidence interval around the estimate to indicate the likely range than to test a specific hypothesis. Therefore, in many situations, it may be more appropriate to choose the sample size by setting the width of confidence interval rather than to rely on the power of the calculation. One more consideration which has to be taken is the allowance or the losses. My friend Atanu will be taking it in a detail. Loss to follow-up occurs in most of the longitudinal study. Individuals may be lost because of the various reasons. Okay, and such losses may produce bias in your study outcome. And generally, it is said that at least if there are reduced power because of the loss to follow-up, generally a 20% allowance has to be taken in sample size calculation when there is loss to follow-up. The calculation for your sample size consideration from loss to follow-up is a specific, entirely different topic that will be taken by Dr. Atanu. Okay, now coming on the different scenarios for the calculation of your sample size. Now, first is the estimating of population proportion. When you are interested in proportion, when your outcome is proportion, and you are making it with specified absolute precision. Okay, so required information for estimating the sample size is as under. You should know about the rough estimate about the proportion for which you want to make the sample size calculation. Desired confidence level, that means you has to fix the type 1 error. Absolute precision D, which you are willing to take. Total percentage point of error that can be tolerated on each side of the figure obtained. For example, if anticipated prevalence of infection of TB in a population is 10%, okay, and you are satisfied if your sample gives you a deviation of 2 points, 8 to 12. In that case, your absolute precision is 2% or 0.02. So this has to be taken first before calculation of sample size. So you have to decide on the value of D, which you are going to take. You have to decide on the value of alpha, which you are going to take, and you have to make a guess about the proportion. That this guess about the anticipated population proportion can be based on the review of literature, can be based on the pilot study which you might have conducted or someone else has conducted, and using these values you can estimate the probable sample size, required sample size. Okay, so if you are knowing these things, you can use this formula for calculating the sample size, which is n is equal to z square 1 minus alpha by 2 1 minus p by d square, where p is the guess which you are taking from the literature or you are taking it from the pilot study. D is your allowable difference which you are allowing in your study. So for example, in a survey which is aimed at estimating the vaccination coverage, P is usually anticipated at 50% or 0.5, and your allowable difference which is allowed is 10%. So D is 0.1, and the level of significance is 5%. The estimated sample size using the above formula is 96 for random sampling. Okay, So in case if you are not having any idea about the population proportion, generally you can always you can do a pilot study. But if you it is not possible to have a pilot study, neither the theory is giving you any idea, then you can take p equal to 50% to have the sample size, because at this level you might be getting a maximum sample size. Okay, so if this is 96 only if you are using the SRS, that is simple random sampling. In your sampling technique, if you have chosen simple random sampling, then it is 96. But if you have chosen a different sampling approach, for example, you have chosen a cluster sampling, or you have used stratified sampling, in that case, what you have to do in that case, design effect comes into place. You have to take the consideration of the design effect. So design effect, what does it do is basically, if you are using a stratified sampling or cluster sampling, there might be intracorrelation between the variables. That correlation has to be ruled out. Okay, so that correlation has to be ruled out. So in that case, we multiply this n with a design effect factor. Okay, generally this design effect factor is taken as 2, but you can conduct a trial study, and you can calculate the design effect precisely, which is nothing but it is sample design variance divided by variance using SRS. That means, suppose you have used a stratified sampling. So by using stratified sampling, whatever the variance you have got in your study for the point estimate, that will be your numerator. Then the same study under different setup of SRS is done, and this time you are getting a variance using SRS. Now whatever the difference you are getting, you would be having that as a design effect. So first time you would be having stratified sampling. That means you would be dividing your population into certain groups such that they are homogeneous within, heterogeneous in between, and you are doing stratified sampling. You are getting some variance. Second times you are not dividing it into any group, just you are using SRS, random number table or lottery method, and you are calculating, and you would be getting some variance. So that difference of the ratio of that variance is your design effect. Okay, so in the same study, if someone has used a stratified or a cluster sampling, then instead of 96, you would be using a sample of 192. Okay, that 2 factor has comes into place to take care of the intra-class correlation. Now, the point estimate of a population proportion with specified relative precision. Okay, that was absolute precision. Here we are having relative precision. So relative precision, the first 2 things are same. We should have an idea about the anticipated population proportion. We will be fixing the type 1 error, and relative precision, epsilon, we are denoting it by that, is the sample result should fall within epsilon% of the true value. So it's a relative term compared to your absolute term. Okay, so in that case, your sample size estimation is having the almost the similar type of formula. Only thing is that instead of D, you are having epsilon square into P. We can have one example from this. For estimating the prevalence of tuberculosis infection among children of age 0 to 9 years in a locality, how much should we include in the sample so that the prevalence may be obtained within 10% of the true value? So here the relative precision is telling that 10% with 95% confidence. That means alpha is 5%. Confidence interval is 1 minus alpha into 100. So anticipated P is here, it is saying that within 5 to 10% we want. Okay, so if it is in a range, generally we should choose a lower value because the lower limit is taken to have a larger sample and a better precision. Confidence interval is 95%, 5% error we are allowing. The relative precision 10% it is saying, so it automatically it will be 10% or 0.1. And using the formula, previous formula, this one, we can put the values z square 1 minus alpha by 2. This z is nothing, this is taken from the normal distribution value. For 95% it is 1.96. Okay, so using this formula, we are getting estimated sample size would be 3457 in this case. Okay, and you can look if someone wish to have this type of study in a community he wants to do a survey, then it has to be multiplied by the design effect. So automatically you can see that if we are taking a community survey, more than 7,000 samples you have to take in your study, which is quite large. Okay. Now, coming these all things we were talking about were one sample situation. We were estimating only one proportion with absolute precision, one proportion with relative precision. There might be two sample situation also. So here we will be seeing the estimating the difference between two population proportion with specified absolute precision. That means we are having two samples, P1 and P2, and you are comparing them and you want to have the adequate sample size for this type of calculation. So suppose we are having equal n in two groups. So what would be the required information which we should have, I guess? First one is the anticipated population proportion, P1 and P2, confidence level, and absolute precision required on either side of the true value of the difference between the proportion D. That means P1 minus P2, if you are having D, you are getting D, how much deviation from this D you are allowing, 2 points, 3 points, 4 points, 5 points, whatever. So in that case, if you are having two sample situation and both the samples are of equal size, in that case, we can use this formula n is equal to z square 1 minus alpha by 2, P1 into 1 minus P1 plus P2 into 1 minus P2 by D square, where P1 and P2 are the anticipated value of the proportion in the two populations. So you are having two groups. One is having a proportion P1, second one is having a proportion P2, and you are planning to have the testing of these two groups. Okay. And for this, you want to have the adequate sample size. So you decided that I should take alpha 5% and I should allow the absolute difference delta, say 4%. Then you can use this formula to have the required sample size value. Okay. For example, let's look at example. What sample size to be selected from each of the two groups of people to estimate a risk difference to be within 3% point of the true difference at 95% confidence interval when the anticipated P1 and P2 are 40% and 32% respectively. So 95%, automatically your Z value is 1.96. P1 it is saying 40% and P2 it is saying 32%. Here it will be P1 and P2. 1 and 2 are missing. So P1 is 40%. So we are having in the formula P1 40%, 1 minus P1 prevalence, non-prevalence. So it will be 60 plus P2 is 32% into 1 minus 32%, which is 68%, divided by 3, which is the risk difference, point difference, which one is allowing in his study. So the required sample size in this case of two proportion difference will be 1953. Okay. Now for the hypothesis testing for the two population proportion. Okay. So here the required information is the difference between P1 and P2, how much you are willing to have the difference, anticipated value of P1 and P2, level of significance, power of the test which you are allowing in your study, and the last one which you have to make the assumption, or we have to fix the thing whether you are going with a one-tailed or a two-tailed hypothesis. Okay, so for one-tailed hypothesis we would be having a different formula. For a two-tailed hypothesis we would be having a different type of a formula. Okay, so for a one-sided test we are having n is equal to z into 1 minus alpha. Here you can look that we are having z is equal to 1 minus alpha only, and here we are having z is equal to 1 minus alpha by 2 because it is a two-tailed one. So we are taking alpha by 2. Here it is only one tail, so we are taking 1 minus alpha only. So it is 2 into p bar. P bar is nothing but it is the average. Okay, so that means proportion in the first P1 plus P2 divided by 2. So this is p bar average. So 2 into p bar 1 minus p bar plus z into 1 minus beta, whatever the power you are allowing in your test, into P1 into 1 minus P1 plus P2 into 1 minus P2, the whole square divided by the difference in the outcome, P1 minus P2, D, which we were saying, or delta, which we were saying in our study, P1 minus P2, the whole square. For two-sided, it is the same formula. Only thing which is different is that the Z value will change. Here we are having Z at 1 minus alpha. Here we would be having Z at 1 minus alpha by 2. The rest of the things are more or less same. So this is example on a two sample situation. So here you can see that it is believed that the proportion of patients who develop complication after undergoing one type of surgery is 5%, while the proportion of patients who develop complication after a second type of surgery is 15%. How large should the sample size be in each of the two groups of patient if an investigator wished to detect with a power of 90% whether the second procedure has a complication rate significantly higher than the first at the 5% level of significance? Okay, so this is a problem. So we have to make certain assumptions. So test value of the difference in the complications rate under the null hypothesis, we would be assumed that both are same. Anticipated complication rate, it is given 5% for the first one and 15% in the second one. Level of significance we have fixed at 5%. Power we have chosen at 90%. And suppose we have, and we are here, the alternative hypothesis is that the how much less complication we are having, higher complication we are having in the first compared to the second one. So it is a one tail situation, P1 minus P2 less than 0. So in this case, we are having one tail hypothesis and we are getting the value of P1 as 5%, P2 as 15%. And using the equation A, this one, first one, we can have the anticipated sample size 153 in either of the each group. Now, estimating the population proportion with for the mean, and we are having with absolute precision. Okay, so here outcome of interest is the mean. So we need to have certain assumptions. First one is that you have to make a guess about the variance, how much variation or dispersion is there in your study sample. That how can you can get it from the pilot study, or you can have an idea about it from our previous review of literature. Then you have to decide on the absolute precision, how much you are going to take, 2 points, 3.5 points. Then you can calculate the sample size using the formula n is equal to z square 1 minus alpha by 2 into sigma square by d square. The sigma is your standard deviation from the pilot study you can estimate. So this is a study, and from this study you can make a guess about the sample size, required sample size. Okay, here it is given level of significance is 95%, and your difference is given at systolic blood pressure difference is 15 to 20, that is the 5-point difference is there, and deviation is 5-point deviation is there, and you have a margin of error 5%. So putting the values of these values in the previous formula, you can make the required sample size. Okay, I hope it can be easily done. So that was on mean for the relative precision. Absolute precision. You can have the relative precision. So in that case, you would be making a information, you requiring the information, guess about the population mean mu, variance sigma square, and instead of D, you would be having the relative precision D. So instead of D, you would be having epsilon, and using this formula, one can make a guess about the required sample size for the mean. Now, the last scenario, we were talking about the mean comparison where we were having one sample situation only. So for the first case, we were having only one sample with absolute precision. We have used that formula. One sample with the relative precision, we have used the second formula. Now you can have the two sample situation, and you want to compare both the groups for the means, and you want to have the adequate sample size. In that case, you are interested in two samples rather than one sample. So you need to have certain informations. First one is the difference in the means, which you are allowing mu1 and mu2. You want to have the standard deviation, make a guess about the standard deviation for the first sample and second sample. But you are having the variation in the first and the second sample, and the third one is the absolute precision D. So when you are having two samples, instead of considering both the standard deviation, we calculate a common variance in your study, variation in the study, which we call it as the pooled variance. So pooled variance is calculated as sigma, denoted by sigma square here. It is equal to n1 minus 1 s1 square minus n2 minus 1 s2 square divided by n1 minus 1 plus n2 minus 1. Okay, so this, using this formula, you can have the pooled variation formula, and the pooled variant formula can be used in this equation, and you can have the required sample size under two sample situation. So this is a problem. Suppose you want to know the sample size equal groups required for detecting a mean difference of 0.3. So here the mean difference or the margin of error is given as 0.3 milligram per ml between well-nourished and undernourished children. This difference is considered to be clinically important. Suppose that the mean and SD of hemoglobin levels available from an earlier study in a random sample of well-nourished and undernourished groups were as follows. Okay, the data is not there. There has to be the data for the mean for the first study and the second study. In studies where the plan is to estimate the mean difference of the continuous outcome, here this question is not complete. We need to have the mean for the both the values. Okay. Then we can easily calculate using the formula, where for the both the samples, if you are having for the first sample S1 you are having, for the second sample S2 you are having, you can calculate the pooled variance using this formula sigma square, and using Z value 1.96 into 2 into pooled variance divided by the your absolute margin of error, which is 3% there, then you can calculate the sample size. So standard deviation for the both samples has to be there. Okay. Sorry. Okay. Now, this is another scenario. Sample size is a very vast subject, and we can have a very big workshop on sample size calculation only. Okay, so I'm just touching the tip of the iceberg only. Okay, just the major points. So in case of a matched sample, we can have a study design which can be case control in nature. In that case, if your outcome variable is continuous one, then how to calculate the sample size? So in studies where the plan is to estimate the mean difference of a continuous outcome based on matched data, the formula for determining the sample size is given below, which is n is equal to z into sigma d divided by e, where here sigma d is nothing but it is the variation in the pre and post. You are having a pre score, you are having a post score, or you are having a score for the cases and you are having a score for the controls. So whatever the difference you are getting for case and control, that difference of the score deviation, that is here sigma d. So sigma d is nothing but it is the difference in the score deviation, standard deviation of the difference score of the pre or post, or for if you are having a matched case control study design, difference of the score deviation for cases and control. So it is, in that case, you can calculate z into sigma d by e. E is the allowable error which you are allowing in your study, desired margin of error. Mostly we are done with this thing.